Hi everybody, this is lesson 7.3 looking at section 2.4, So before we have covered increasing and decreasing functions, and now we looked at increasing and decreasing rates of change, which are not the same thing. So for functions, if the slope was positive, well, the function was increasing. If the slope was negative, then the function was decreasing. For rates of change, we are looking at the values of the slopes as we move from left to right. So the rate of change is increasing if it moves from negative infinity to positive infinity on a number line, and it is decreasing if it moves from positive infinity to negative infinity on a number line. We looked at 4 different examples here. So we have this curve that opens downward. This is home right here at the base where your x-axis is. So you can see there's a strong slope here that's positive because we're increasing, and then it becomes weaker, so that slope gets a little bit weaker as you go away. So that means that we're decelerating away from home because we're going away from this base. The function is increasing, however the rate of change is decreasing since this is open downwards. Over here, this is home, we're coming towards home, and this is a weaker slope, this is a much stronger slope, so we're accelerating towards home. The function is decreasing since it's coming down this way, and the y values are getting a more negative or smaller, and the rate of change is also decreasing since this is open downwards. The last 2 examples here, we have this curve where it's a strong negative slope to a weaker negative slope. We're coming towards home since this is a stronger slope and this is weaker. We're decelerating. The function is decreasing and the rate of change is increasing since it's opened upwards. And then over here we're accelerating away from home. It's a weaker slope to a more stronger slope, so the function is increasing since it's going to greater y values, but the rate of change is also increasing since it's opened upwards. Then we investigated the distance and rate of change looking at different intervals. So what we did here is we broke down every single interval from A to B, B to C, C to D, D to E, E to F, F to G, and G to H. So every time there was either a turning point or a change that occurred over the distance over time. So to do this, we looked at AB, which is our first point. So we plotted the points for each one, which is going to be your 7 minus 0 over 0.4 minus 0, and that gives us 17.5. So what we can see here is that this is actually open downwards. So our rate of change is decreasing and we are decelerating away from home. Much steeper slope right here, and this is a little less steep. Then we go from B to C. So B to C, you take your points just like before. You have your y2 minus your y1 divided by your x2 minus x1. It gives us 0.83. This, however, is linear. Anytime you have a linear line, it's a constant speed. So we're not talking about accelerating or decelerating when you have a linear line. It has to be more of a curved shape. So this case is a constant speed and we're still going away from home. However, at C we have a bit of a turning point and we are coming towards home. We're coming back down. So it's still a constant speed because it's a straight line. Then D to E, we again take your y2 minus your y1, y2 minus your y1, and you have approximately negative 5.38. Well, you're coming towards home. You're going to have a negative slope just like you have in BC and DE when you're coming towards home, and CD. You will have a positive slope if you're going away from home. Now we're decelerating here towards home. From E to F, we just stopped. So we're staying here at home for an hour. Then from F to G, we will do your y2 minus your y1, your x2 minus x1, and that gives us a positive 2.54. So we are going away from home. But the slope here, it becomes curved, and then we have a turning point. So the last one here, we're coming back home. We have G, which is your y2, 0 minus 3.3, and 6 minus 5.4. So we're going to get a negative 4.71, which tells us we're coming towards home. And that's how you would look at investigating the distance over time, which is speed, on this interval graph. In example 2, we wanted to locate any max and min. So we have 2 mins at x equals -1 and x equals 3.3 approximately, and then we had 1 max at x equals 1.5. Then we describe the function, just the function, not the rate of change. So when we look at the function is increasing from here, -1, all the way to 1.5, because here we have a turning point. So we're going to write -1 to 1.5. Then we have our turning point, we decrease, and we have another turning point at 3.3 where we increase all the way to positive infinity. When is the function decreasing? Well, from negative infinity all the way to -1, because that's a turning point, and then we increase here, and then we have another decrease from this turning point, 1.5 to 3.3. Points of inflection, so anytime that it passes through any of the axes here, that will be a POI. Lastly, we describe the rate of change. So remember, rate of change is increasing when it is opened upwards. So when is this opened upwards? Well, from negative infinity all the way to 0. And then it's going to be opened upward again from about 2.5 to positive infinity. Lastly, when is it decreasing? Our rate of change is when it's open downward, so it's open downward from 0 to 2.5. So next we assess looking at global and local maximum and minimums and so on. So what does this mean in terms of IROC, your instantaneous rate of change? Well, a maximum occurs when the function goes, a positive slope to a negative slope, and your IROC will be 0 either at your max or your min, and your min will be negative and then positive slope. In this example here, we looked at the height of a tide in Nova Scotia that can be modeled by this sine function, where t is the time in day in hours, and we wanted to use our h value in this course is 0.0001 on the left and the right hand side, using difference quotient. So this can help us determine the rate of change at the tide at 11 p.m. Well, we're looking at a day in hours. 11 p.m. is also represented as 23 because it's the 23rd hour of the day. So we'll say t equals 23. Whenever you're doing these types of problems, you want to look at your left side and then your right side. So your left side, you'll have h equals -0.0001. So you take the 23 and you subtract that to get your new h value here. So now we can use our IROC equation that we've already used previously in other lessons. So h of 22.9999 minus h of 23. We just plug in h into the equation to get these values here. Make sure that you're leaving enough space for your decimals. So if this is 1, 2, 3, 4, 5, 6 numbers, you're going to want 1, 2, 3, 4, 5, 6 decimals if this is an infinity number and it keeps going on and on and on in your calculator. Now, we have that there. We just subtract all of this and we get approximately -0.01. We're going to do the exact same thing to the right side. So the right side will be h plus 0.0001. So that's 23, our t value, plus that. And we plug it into our IROC equation. These numbers go into our h of t. And then we subtract it and we should get plus 0.01. So these numbers here should show us how it's coming from the left and the right side. Well, negative means that it's a negative slope, and then positive means that it's a positive slope. So it's going down and then it's going up. Down and up, we know, is a minimum. So a minimum is occurring in this case. So we can say, since rate of change approaches 0 and the function goes from decreasing to increasing, we can say that there's a minimum at 11 p.m. The last example we did was proving that there's a maximum value for this quadratic when x is equal to 3. So we'll use 3 and approach it from the left side and approach it from the right side. So from the left side, it'll be negative 0.0001, and the right side would be plus 0.001. So just like before, plug it into your IROC equation, plug these values into your f of x, and then you should get positive 0.01, and on the right side, you'll get negative 0.01. So what this tells us positive is that we are increasing, so an increase in slope, and the negative, we're decreasing our slope. So this is the maximum, and therefore we can prove example 4. So since the rate of change approaches 0 and the function goes from increasing to decreasing, we say there is a maximum at x equals 3.